for today's distinguished webinar series in AI and Cyber. Today's distinguished speaker is Dr. Yuzhang Lin. The title is Enhancing Cyber Physical Resilience of Smart Grid. And Akshay, could you show the bio? Dr. Lin is an assistant professor in the Department of Electrical and Computer Engineering at New York University. He obtained his bachelor and master's degree from Tsinghua University, Beijing, China, respectively, and his Ph.D. degree from Northeastern University, Boston, Massachusetts, where he received the university's prestigious Outstanding Graduate Student Research Award. His research interests focus on smart power grids, particularly in the aspects of data-driven modeling, situational awareness, cyber-physical resilience, and machine learning applications. He has published 5 book chapters and more than 50 journal papers, and his research has widely supported by NSF, DOE, ONR, NYSERDA, national laboratories, and power industry. He currently serves as a co-chair of the IEEE Power Energy Society Task Force on Standard Test Cases for Power System State Estimation and the secretary of the IEEE PES Distribution System Operation and Planning Subcommittee. Dr. Lin is an associate editor of the IEEE Transactional Power Systems. He's a recipient of NSF CAREER Award. Dr. Lin, it's a great honor to have you as part of the Center Distinguished Webinar Series. Thank you so much for spending your time this morning with us. The floor is yours.
Yeah, thank you so much, Rikesh, again for the invitation. I'm really glad to be here to share our recent research findings. So let me start sharing. So are you able to see that?
Yes, we are good. Yeah, please.
Okay, perfect. Thank you. Yeah, so today my topic is resilience of cyber physical power systems or smart grids, we call this these days. Now, first of all, I'm not a real expert of cybersecurity. I'm more of a power and energy person. But today, my perspective is to look at sort of the interaction between the cyber, or we can say information system, and the physical power system, and see how we can improve, its performance as a whole, especially during high impact events such as extreme weather or natural disasters or malicious attacks. So now, first of all, please allow me to introduce our team a little bit. My name is Yuzhang Lin. I'm assistant professor at NYU. So at NYU, we have 3 faculty members working in the power and energy area. So we work on all aspects, modeling, monitoring, stability, control, and optimization. And these days, we also work a lot on AI applications. We also work on hardware like power delivery equipment. So we have a power lab with heavy equipment such as electric machines and transformers, cables, power electronics, measurement devices, as well as some high performance simulation servers.
Do you
Uh,
have Opal RT or do you have RTDS? Do you have?
Not yet. Actually, we are planning to deploy RTDS in the next couple of years. Yeah, as you know, I just moved to NYU 2 years ago, so it is in my plan, but I
That's good.
still haven't find time to do it. Yeah, but before I was here, there was already lots of heavy equipment and simulation servers, and hopefully they will all be connected together through the hardware in the loop simulation. So we receive funding support widely from NSF, DOE, multiple offices of DOE, ONR, and NYSERDA, as well as the power industry. We work a lot with the utilities in New York State. There are, I don't remember, 7, 8 utilities in New York State, and we have pretty good relation with them. We have DOE as well as NYSERDA projects together with them. And we also work widely with national labs. Um, okay, I guess that's it for the introduction, and I would like to move on to today's topic. So I'm going to talk about resilience. So what do we mean by resilience exactly? Everybody is talking about this these days. So if we look across the government definitions as well as the literature, we all find different definitions, but they basically mean the same thing. That is the system's capability to respond to and bounce back from high impact events or disturbances. So this could be best described by this resilience curve you can see here. So let me use the laser pointer. So you can see this resilience curve. So this could be defined for any engineered system. As long as you define a certain functionality metric and you plot it against time before, during, and after the disturbance, it looks something like this. So so resilience means that the system can sort of limit or absorb the disturbance and limit the degradation of the functionality when it happens. And also after the clearance of the disturbance, it should be able to recover pretty quickly. So that's what we mean by resilience. That's quite straightforward. So what are the means of improving resilience? So we can do different things before, during, and after the disturbance. So before the disturbance, although nothing has happened, we can, act ahead of time and make our system stronger, or we can pre-dispatch the resources such that we can react quickly when the disturbance really strikes. And when it really strikes, then hopefully the system can adapt quickly, so it can use the remaining resources to reconfigure the system and limit the degradation of the functionality, especially if we want to keep some really essential functionality. And then after the clearance, we'll try to restore the system. So usually our resource is limited, but how can we wisely use it to recover the functionality as quickly as possible? So that's what we can do afterwards. But mathematically speaking, we can say that enhancing resilience simply means we try to push this curve up. We want to push it up as much as possible. So we have little degradation and very quick recovery. So it means that we are trying to maximize the area under this resilience curve. So that is this shaded area. We would like to maximize this area, or mathematically we can say we try to maximize the integral of the functionality level over time during this entire process. So this is a sort of a general definition for any engineered system. So with that in mind, so now we can sort of look at what we mean by resilient system versus a non-resilient system. If we have a resilient system, you see the functionality drop will be limited and then it goes back very quickly. But if the system is non-resilient, it means that you have a large drop and then it recovers pretty slowly. Okay, so now with that in mind, now we can talk about electric power systems. So for those of you who are not familiar with this, we are talking about a system, a critical infrastructure at a national scale. So it connects all the generation facilities to the customers, to the loads. So here you see the sort of the backbone transmission network of the power system in the United States. It doesn't include the local network, which we call the power distribution system, but you can see that it's already quite large scale and complex. In this system, you need to keep the instantaneous balance between the generation and the load while respecting all the network constraints. So it's a very complex system to operate. What makes things worse is that this kind of huge system is constantly under threats of either internal failures or external disturbances. So you can imagine such a system has maybe hundreds of thousands of components. So even if the probability of failure of each component is very small, we still constantly see components failing here and there. So we always have internal failures. And also we have external disturbances like extreme weather events, natural disasters, or even malicious cyber or physical attacks. So if they are not well handled, they could lead to blackout events, meaning the customers will lose power and our modern society cannot function. So just to show you some well-known blackout events. So in 2017, there was a hurricane sweeping through the island of Puerto Rico, and it effectively uh, wiped out a large part of the power system. So here you see the sort of a satellite image before and after the hurricane, and you see that a large part of the island lost its electrical supply. And actually, it took a very long time for the power system to recover. There are some customers who still didn't have power back a few months later or even a couple of years later. Um, and just earlier this year, there was a massive blackout event in Europe. So because of some small initial faults and not enough capability to control the grid frequency and voltage, it finally leads to a total blackout in Spain and Portugal. So the whole country is down for nearly a whole day. Until the power system restoration is complete. So you can imagine it affects all aspects of modern society. It's life-threatening and also it's associated with a huge economic losses. So blackouts cannot be totally avoided, but when it really happens, what we need to do is to find a plan to restore the power system as quickly as possible. So at least we can limit the duration of the outage. Okay, so that is why power system restoration has been a very important topic for nearly a century. If we look at the literature, the earliest research regarding power system restoration dates all the way back to the 1940s. Traditionally, after a blackout event, the power system restoration has three steps. The first step is called a generation startup. So not all the power plants can self-start. Some power plants require external power supply to start. So that's why the first stage is always to have some generators, which we call the black start units, which are the units that can start themselves without external power supply, to start first. And then we need to energize some transmission lines such that the power, we call this cranking power, to go to the other power generators which cannot start themselves to help them start. So this is called a generation startup. And then with enough generation, we would like to energize the transmission network. We need to switch in the lines one after another until we get a skeleton network to connect the generation to the loads. And then finally, the last step will be the load restoration. So we would like to switch in the loads block by block. We cannot switch them in all at once because remember, we have to keep the generation and the load balanced at any second. So we have to do it gradually and carefully respect all the network constraints such as power flow, frequency, and voltage. So each of these steps usually contain multiple sub-steps. You have to do it sort of, sorry, there's something wrong with my pointer. Yeah. So each of these steps contains multiple sub-steps. So it's a classical sequential decision-making process. Okay. So the restoration, power system restoration was studied actually much earlier than resilience. Resilience only becomes a big concept in the recent years. But if we check the objective of power system restoration against resilience, we find that they match each other almost perfectly. So first of all, the restoration, power system restoration handles the third stage. That's the post disturbance stage. It doesn't look at the pre disturbance or during the disturbance, but it looks at what we can do after the disturbance. And the objective of power system restoration is to maximize the cumulative power supply over time. So if you remember in the first slide, I said that for any engineered system, we can define a functionality metric. So here for power system, if we just define its functionality as the total amount of generation capacity or supplied load, then the objective of power system restoration is exactly to maximize this shaded area, the area below this curve, this functionality curve, which is now defined as the generation and the load. So in this sense, power system restoration is totally compatible with the resilience concept. Okay. So what's new here? So power system restoration has been a study for a long time. But as we know, in the past, the power system works just fine. We have stable power supply, and we didn't hear people talking about this. But in the new century, the power system is facing a lot of challenges as we try to make our power generation fleet clean. We integrate lots of wind and solar generation. So that's on the generation side. And on the demand side, we are also trying to electrify the transportation and building sectors. So we are integrating lots of electric vehicles as well as heat pumps. So the wind and solar on the generation side and EV and heat pumps on the load side, they introduce lots of uncertainty and variability to the power system, making the power system much more difficult to control. And also the system is becoming distributed. So we have many small distributed energy resources gradually replacing those large centralized power plants. So they have a sheer number and they're difficult to monitor and control. And finally, the system is becoming more heterogeneous. So we have all different kinds of components that have different dynamic behaviors, which also add to the challenge of grid stability and control. And because of all these challenges in the 21st century, we have been installing lots of sensing, communication, control, and computing devices, trying to make the grid smarter, right? So that's why we are talking about smart grids these days. But this, of course, brings a lot of opportunities. It makes the power system, more intelligent and autonomous. But it also brings in new vulnerabilities. So now the system looks like this. We have sensors collecting data from the power system, and then we need a communication network to send the sensor data to the control center, where we have powerful computing resources here, and we make decisions, and then we send the control signals out to the local controllers of the power plants or substations, which controls the physical components. So unfortunately, when we have disturbances, they're likely to impact both domains. So for example, natural disasters, they could not only take down power lines, but they could also take down communication links or nodes, right? And on the cyber network, we might even have malicious, compromises which could make our cyber network more function and affect its capability to monitor and control the physical system. So when there are high impact events, it's likely that you will have damages or compromises, not just in the physical domain, but also in the cyber domain. So that's the new challenge. And if our cyber domain is partially down, it could affect a lot of things. For example, we will lose sensor data, so the control center no longer receives sensor data. So this means that we no longer know what's going on, and we have to operate our system or restore our system based on assumptions, and this could lead to lots of violations which we don't even know, and finally that may lead to failures in your physical system restoration. And we may also lose the capability to control our devices. So we lose the means to send out control signals. So we may lose the capability to dispatch our generators. So we may not have enough resources to pick up the loads or regulate the voltage in the physical system. Unfortunately, if we look at the power system restoration strategies nowadays, most of them have the underlying assumption that the cyber network is intact. It doesn't have any problem because we usually assume that we know everything. But this requires the implicit assumption that your sensor data are still available at the control center. And we also assume that once we solve our optimization model, we get the optimal decisions. We can always execute our decisions. But this also relies on a functional cyber network because you have to, send out your control signals effectively. So this kind of underlying assumption of a fully functional cyber network may not be always realistic in the real world, and if it is not, then this will render the power system restoration plans ineffective. Okay, so now we know the importance of a cyber network in power system restoration and resilience. Now, the next question is how can we incorporate it, right? So now the cyber network or communication network restoration, traditionally it's not within the scope of power engineering. But because resilience is also a big deal in other areas such as communication, networking, and cybersecurity. So there are lots of existing work in those areas, as we can imagine. So here, for example, I'm showing one paper which studies the optimal restoration plan. Sorry. Yeah, which studies the optimal restoration plan of the backbone communication network of North America after major disasters, basically to decide on the sequence of restoring the communication links to recover the data traffic as quickly as possible. And also in the cybersecurity domain, even though there's no sort of optimization model established on this decision-making problem, there are indeed very well established procedures for restoring a cyber system after it is under attack. So the question is, if those solutions are already available, why do we still care, especially for us, power and energy people? Why do we still care? Can we just borrow the solutions from the other domains? So the reason we care is that if we directly borrow the cyber network restoration strategies from other areas, the objectives there usually is to maximize some general cyber network metrics, for example, the data throughput, the latency, or the number of devices you can secure, as the objectives. But maximizing those general objectives may not maximize the benefit for power system operation and control, because that requires lots of domain-specific knowledge. Especially so many electricity utilities, they own their private network. So their cyber networks are not the public ones. So those networks are just for serving the purpose of operating the power system. So if they are dedicated networks, then it means that their restoration strategy should exclusively serve the objective of power system operation and restoration. But because of the traditional gap between different areas, this problem has not been well addressed. Okay, so this is why we advocate a integrated cyber physical power system restoration planning. So in the physical grid restoration, we just follow what's already available, right? So we define the physical power system's functionality as the generation capacity or the loads. And once we define that, we have our resilience curve and we know what to maximize. That's what's under this curve. But then the question is, how should we define the functionality of the cyber network, which we aim to maximize? As I said, we don't want to take general metrics because they may not be the most beneficial for power system operation. So our proposal is that since the cyber network is supposed to serve power system operation, then we should take the observability and or the controllability that the cyber network can provide to the physical power grid as the restoration objective or the functionality metric for the cyber network. So only with that, so we can make sure that the cyber network restoration actions are oriented towards the most benefit to the physical grid restoration. So with that, so we can divide this integrated restoration problem into two subproblems. So in the cyber domain, we should have a controllability and observability oriented restoration, meaning that the restoration actions should maximize the controllability and observability of the physical power system. And then in the physical domain, the restoration should be controllability and observability assisted, meaning that you should actively use the regained controllability and observability from the cyber domain to improve the restoration process in the physical domain. Okay, so that's how they are interrelated. So for both domains, the mathematical formulation of the objective is still the same. It's to maximize the integral of the functionality over time. But the only difference is that the definition of the functionality is different. So for the power system, it's generation and or load. And for the cyber network, it is observability and or controllability. So that's our key insight here. Okay, so with that, the next question is, of course, how can we define observability and controllability, right? What do we really mean by that? So let's first talk about observability. So observability is something very well studied in power systems. It is a prerequisite for so-called power system state estimation. So state estimation takes all the sensor data and try to figure out the most probable state of the power system, and it is the foundation for most applications in the energy management system. So the observability of a power system is determined by multiple factors, including the sensor location, type, as well as its functional status, meaning whether it's damaged or compromised or not, right? And it's also determined by the topology of the power system, as well as the topology and the functional status of the communication network. So here, I'll give you an example of phasor measurement unit, which is a kind of sensor in power systems. So if we install a phasor measurement unit we call PMU at one bus of a power system, then it can directly measure the voltage phasor of this bus. And because the voltage phasor is exactly what we call the state of the power system, so we can say that the PMU here can make this bus observable. And the PMU can also measure the outgoing currents along all the transmission lines which are connected to this bus. And if we also know that current, and we also know the impedance of the transmission line, it means that we can also estimate the voltage phasor at all the neighboring buses, meaning that all the neighboring buses will also become observable. So from here, you can see that the observability of the power system, or buses is highly dependent on the location of the sensors as well as the topological connection of the power system. But that's not the whole picture. After the PMU collects the data, it also needs to find a path in the communication network to send the data to the control center. So it becomes available at the control center. So that's how we can make it observable. So this means that the observability is also dependent on the topological connection as well as the functional status of the communication network, which is our cyber network. So that's how we can find out observability. So if we want to come up with an observability metric, we can, of course, count the number of observable buses or branches. But because different buses or branches may have different importance, so we come up with a better metric, which is observable power. So because different buses and branches, they process different amount of electric power, and of course we would like to observe more power flow in the power system, right? So depending on which buses and branches are observable, we can calculate the total amount of observable power, which we can use as the metric to maximize in the cyber network restoration. Okay, so next we also have controllability. So controllability is not so well defined in power systems because of the complexity of control problems in power systems. However, in the power system restoration, we do know that our priority is to have enough controllable generation capacity to pick up the loads as well as to regulate the voltage. So based on that, we can construct our controllability metric. So the control of the generators are typically done by the so-called automated generation control AGC, or automated voltage control AVC, and they require control signals to be sent from the control center to each individual generator. So certainly you need to have at least partially functional cyber network to do that. So the controllability is determined by the capacity and ramp rate of the generator, as well as the functional status of the local controller of the generator, as well as the topology and the functional status of the communication network. So with these three, we can sort of calculate here what we call the controllable power, right? So how much power you can control and dispatch based on the status of the cyber network. And here, one detail is that the controllable power may be different in the short term versus in the long term, because in the short term, the controllable power is mainly constrained by the ramp rate of the generator. So the generators cannot ramp up or ramp down their generation instantly. It needs time. So between two time steps, how much can it ramp up? That will determine our sort of controllable power. But in the long term, without the time constraints, and then the controllable power will only be limited by the capacity of the generator. Okay, so I have roughly described what we mean by observability and controllability. Now we can look at um, what we should do in the cyber domain restoration. So here the assumption is that we have an attack or a natural disaster which takes down a large number of components, but we have limited resources to restore them, so they cannot be restored all at once. And we have to come up with a proper sequence of restoration actions such that we can maximize our objective function, which is the cumulative observability and or controllability. So here I'm just listing some typical uh, restoration resources which may be limited. For example, you might have limited number of repair crews or spare parts, like if the devices are actually damaged by natural disasters, then you have to repair or replace them. And if it is a cyber compromise, right, then you also rely on your cybersecurity experts as well as your rebuild or testing environments and your forensic resources to recover your system. But all of these are limited. And here I'm also listing the typical kind of restoration actions. So for physical damages, for example, you have a cable cut, and then you have to repair or replace the damaged or faulted components. And you also have to sort of restart the components which are good, but they were shut down because of the other faults. And if it is a cyber event, it also means different things depending on the kind of a cyber attack. For example, you might need to apply security patches or update your firmware. You might need to recover your lost data. You might want to rebuild your system. You might need to perform remote attestation to check if the remote devices are secure or not. But all of this takes time, also takes resources. So here I'm again showing an example to see why an optimization model is necessary. So for example, in a power system, if you would like to recover the observability of a bus, and you have multiple PMUs at its neighboring buses, and the restoration of any one of them will give you the observability of this bus. So this means that based on the power system topology, you have multiple choices. And then once the PMU is back, they also need to have a functional communication path to send its data to the control center. But you might also have some of the links and nodes here maybe being damaged or compromised. And you also have to make decisions here, like which ones you should recover first, such that you can recover the observability of this bus as quickly as possible under limited restoration resources. So there are lots of decisions to make, and you can see this is only one bus, and we need to coordinately, consider the recovery of observability of all these buses. So as you can imagine, this will be formulated as a quite complex and large-scale optimization problem. Okay, so now, because of the limited time, I can only talk about the concept at a high level, and I cannot show you the detail of mathematical formulation. So now we have to move on to the other domain, which is the physical domain, right? So how can we restore the power system? So it's pretty much the same as the traditional power system restoration. The only difference here is that we should actively make use of the regains of observability and controllability, over the cyber network to constantly improve, update our restoration strategy. So here, with the gradually regained observability, we'll know more and more about our power system, and we can use this capability to, refine our assumptions and make sure that our restoration actions do not cause any security violations. So our physical power system restoration will become more secure. And then as we gradually regain controllability, we have control over more generators and capacitor banks. So that means that we can add them into the optimization model as new decision variables. So we can, we can use their capability to pick up more loads or regulate the voltage more tightly. So here I'm giving you an example how observability can help improve the security of physical power system restoration. Say initially you have lots of compromises or damages on the cyber network, so you lose access to all the sensors. So basically, in this case, you have to restore your physical power system blindly. You don't know anything. So the amount of loads or the amount of power flows are all based on assumptions or historical data. But as you start to regain access to some sensors or you make them secure, you can trust their data, then you can use them to improve our assumptions. For example, if we recover this sensor here, we can measure the power flow along this transmission line. And we find that the measured flow is different than our assumed value, right? So it means that there must be some inaccuracy in your assumption. Probably your assumptions about the loads are not accurate. So then based on these two the discrepancy between these two, you can refine your assumptions about these loads, right? For example, the measured flow is lower than assumed. It means that probably you have less load than we expect, and we can make the correction to have a more accurate assumptions about the loads. So that is one way. And the other way is if we recover uh, the uh, the sensor for measuring the load of a bus, right? So we exactly know what it is. And there are loads at other buses which are still unknown. But historically, we might know that there are strong correlations between the nodes of different buses. So now because you know this, you can better infer what the loads at the other buses are based on their the historical correlations between them. So we have statistical or machine learning methods to do that. So um, here we are showing these two different ways of using our observability to improve our assumptions about the system. And of course, if we have full observability, right, then you know everything and you're all good. So here we are just showing one numerical example we conducted. We show how we can gradually reduce the uncertainty of loads, right? So you see initially we have quite some uncertainty here, but gradually as we receive more information, the confidence interval will shrink, meaning that we are becoming more certain about a load. Okay. So that's observability. And for controllability, how it can help with the power system restoration, that's more straightforward because as we can control more generators, of course, we have more resources to pick up the loads. So it will accelerate the restoration speed. So I'm not talking about the details here. Okay, so finally, the cyber network restoration and physical system restoration, they have to aid each other, right? So we need to carry them out in a sort of iterative fashion. So our cyber network restoration have to be adjusted based on the evolving demands of observability and controllability of the physical power system. While as the physical power system restoration plan needs to be adjusted based on the evolving observability and controllability provision from the cyber network. Okay, so that's what we propose. Okay, so finally, I would like to show you some case study results. So our first study is in the IEEE 39 bus system. So the goal is to study the impact of observability on the physical power system restoration. So here we design two scenarios. In the two scenarios, the cyber network, we assume that the system has full controllability, okay? But they have different levels of observability, and we would like to see how that will impact the system restoration. So the figure on the right, we are showing two sets of curves. So the solid curves shows the load recovery process. So basically the supplied load over time. And the dash curves show the number of security violations in the power system as we progress in the physical power system restoration. So we can see that the main impact of observability is on the system security, right? Because if we don't have observability, we have to restore the system sort of blindly, and that will lead to a lot of security violations. But if you have a much better observability to the system, you can monitor what's going on in the system. So that will limit the number and severity of the security violations. But the observability has a little impact on the speed of restoration, because whether you see the system or not, you can just do whatever you want, right? So you can just try to restore at the same pace. So it doesn't affect the speed of restoration, but the security of restoration. And then the second study is the opposite. We would like to look at the impact of controllability. So here we assume that we have two scenarios, both with full controllability, but they have different levels of controllability. So here we see that the controllability doesn't affect the system security much, because I mean, if you have lower controllability, meaning that you cannot control many generators, it simply means that your load pickup plan will be more conservative, right? So it's not going to destroy your security, but it does make your restoration process slower, right? Because you just don't have enough resources to pick up the loads. So here we can see that the controllability mainly affects the speed of restoration, not the security. And it might even impact the completeness of restoration, because if you don't have enough generation capacity, you may not be you may not even be able to pick up all the loads. So your restoration may be incomplete, as we will see in the next study. Okay, so this is the last one. We would like to validate the benefits of carrying out integrated restoration plan. So here we compare our proposed integrated plan against two baselines. So the first baseline totally ignores the role of the cyber network. It doesn't do anything in the cyber network. And the second one integrates the physical restoration with the cyber restoration. But in the cyber domain, we assume that there's no effective optimization model to guide the restoration. So the resources are sort of dispatched randomly. So here we are showing how the observability and controllability change over time under these three strategies. And we can see the green curves show the physical system only strategy. So if we don't do anything on the cyber network, then of course we'll have a fixed level of observability and controllability. And then the orange one shows the sort of a random restoration on the cyber network. You can see that the observability and controllability both grow over time, but it's sort of slow. And then the blue curves shows our strategy. As you can see, with the optimization model, we can wisely use our restoration resources to recover observability and controllability pretty quickly. So then how would that help with the physical power system restoration, right? So here again, we are showing the comparison between these three methods. So first, we can look at the security, right? So if we don't do anything on the cyber domain, then we don't have much observability, and we are sort of blindly carry out our physical restoration plan, and there will be lots of violations. And this is followed by the random approach, right? So the random approach is a little better because you see the observability gradually gets better, so you have fewer violations. And then our proposed method, because it recovers observability most quickly, so the number of violations is the fewest. And then we can also look at the restoration speed, right? So that's mainly determined by the controllability level. So here you can see that our proposed method can recover the resupply the loads in the shortest amount of time, followed by the random cyber restoration method. And the worst one is the method with the physical restoration only. So here you see we have a incomplete restoration, because if you don't improve your controllability, finally you will not have enough generator to pick up all the loads. So your physical system restoration will actually be incomplete, right? So that's all I have. Finally, I would like to quickly summarize the takeaways. So lesson number one, in the physical power system restoration planning, don't make the assumption that the cyber network is fully functional, right? So this is usually not considered by power people. They just assume that they can know everything and control everything in the restoration process, but this may not be available if your cyber network is compromised or damaged. So you have to consider that in your restoration plan. And lesson number two is don't plan the cyber network restoration alone. Okay, so don't use the general metrics to quantify the functionality of the cyber network, especially if it is a dedicated network. You have to sit down with the power system engineers to figure out what they really need. So here we generalize the needs of power system operation as the observability and controllability levels, and we have shown that they can effectively improve the power system restoration process. And finally, through our simulation results, we found that the observability mainly helps improve the restoration security, while as the controllability improves the restoration speed and completeness. So that's all I have. Because of the limited time, I have to keep everything at high level. So if you are interested in this topic, you can take a look at our publication. So I'm just listing some selected papers here for you to look at. And so we have some more papers that are under review, and we expect that they will appear in the next few months. So also feel free to check after a few months. And I would like to thank my collaborator, who is my former PhD student, Dr. Shamsun Naha Adib. So she developed lots of work, and lots of credit goes to her. And she's now an assistant professor at Montana State University. Okay, just to make sure that she gets the credit. So that's all I have.
Thank you, Dr. Yuzhang, for a great presentation. So I think we'll open up for Q&A, and folks can put the Q&A on the chat. I think, it's interesting to, maybe I'll start with a couple of questions. And I think you touched upon the definition and the relation. But no, when I listen to you, oftentimes I see controllability is a function of observability, and you know, uh, how do you model? And you showed some graphs and relations, but mathematically, how do you relate them? Is there any particular dependency? I'm just curious to see what is the relation that you use.
Yeah, so thank you for the question. So actually, observability and controllability are two sort of independent metrics. So one is not the function of the other. So I guess you might be
So
referring
when
to
when
the
when when people
function.
talk about more and more PMUs are deployed, it's going to increase the observability, right? And which means that whether you have extreme weather event or whether you have cyber event, it is going to give the observability, which means the system operators can jump in and do whatever the action they need. Which may in turn, you're right that controllability is going to increase the speed, but Anyway, I'm just curious to see how, what type of modeling you do in this function,
Yes,
Yeah.
yes, I totally understand. So in reality, controllability and observability, of course, they work together. So if you want to close the control loop, then you need observability. You also need controllability. So observability means uh, whether you can determine the system state based on the measurements. So it's like the earlier part of that closed loop. And then controllability means once you know the state, are you able to control it, right? So it's the second part of it. So I didn't show how we calculate them here. So the way I just described is sort of the classical control theory definition of observability and controllability. But so we also figure that this kind of a classical definitions do not directly apply to power systems. So in power systems, for example, for observability, we care more about like which part of the power system is observable. So we have to sort of define the observability for each individual bus and each individual branch. So it's more of a topological analysis to see where the sensors are and what they can measure and how they are related through the topological connections of the power system to figure out uh, which buses have their states being observed. So that's how we figure out observability. So it's more of a topological analysis. And for controllability, now uh, the issue is that there are multiple control tasks in power systems and they are different. So for frequency control, we only have like one frequency for the whole system. So when we pick up the loads, we want to make sure that you have frequency stability. So that depends on the available capacity of generators across the whole system because all the generators can help control the same frequency. But for voltage, it's a different story because you have different voltages at different buses, and the control of the voltages is more sort of local. So this is why there's no sort of universal way of defining controllability in power systems. So here we just look at how to define controllability such that it is useful for the restoration process. Um, so the way we do that, actually, I'm not showing the details here, but the way we do that is we construct sort of local um, optimization problems to figure out uh, how much the available and controllable generation capacity and ramp rate can help with the low pickup and voltage regulation. In other words, if this generator becomes controllable, then we will have some new generation capacity. Then how much of this capacity can be used towards low pickup? So sometimes it cannot because if the generator is already in a quite congested area, even if it becomes available, you have the capacity, but you don't have the transmission line capacity to send the power out. So it will not be helpful with the low pickup. So yeah, so long and short, so we have to construct a
Sure.
local optimization problem to figure out how it's going to help with the low pickup and voltage regulation. Yeah.
In your IEEE test cases for this 39 and 68 bus systems, or, did you even look into the restoration time between a physical event or maybe a cyber event? Do we really know, what these numbers mean in terms of restoration? I do like that 1940 definition of restoration, how it relates to close to resiliency. But do we really know? I don't know. I haven't looked into this in literature. Do we really know how the restoration speed or time between these two different events, physical and cyber?
Yeah, sure. That's actually a great question. So what we do in this simulation is that we divide the time horizon into 5-minute intervals. And we assume that every 5 minutes we can, take some actions. So this is sort of borrowed from the traditional power system restoration because you can, pick up loads step by step, and each step is several minutes. And for the cyber network restoration, it's actually quite diverse. It depends on what kind of attacks and what kind of resources you have. You might have very different restoration times. For example, if it is just a matter of sort of reconfiguring and rerouting your data traffic, maybe it's just a couple of seconds.
Sure.
If you have some severe compromises, right, and you have to have cyber experts to look into it, it might be like much longer, like minutes or even hours. So what we do is that I mean the way we do it is still sort of abstract, but the way that this kind of optimization model can actually help with the utility is that the cyber experts have to sit down with the power system engineers and figure out, so for example, for each type of events and for each type of devices, what is the estimated time for a restoration, right? So what kind of practices are needed? So they can figure out, for example, how many time intervals it requires to restore the system. Does it require 5 minutes or 10 minutes or 15 minutes, right? So that's how it can be modeled into this optimization formulation. Yeah.
Sounds good. We have one question. Gupta, do you want to ask that question directly? Are you there? Or maybe I can read this. If attackers intrude into cyber network and damage its physical counterpart somehow, then is it impractical to say that for power system restoration, just the effect of attack on cyber should be nullified? I don't know what uh,
I guess it probably means what happens when there are some kind of propagation
sure.
between two areas.
Let's go to the Dave's question. Are you using any AI models to predict outages from indirect data, or are you looking at external data points to predict data domains that influence recovery from outages?
Yeah, so for this particular work, we didn't use any AI. It's sort of a classical optimization model. And we don't really do a prediction of outages here because here our focus is on how to restore after things happen. So outage prediction is usually, it is also a means of improving system resilience, but it is usually carried out before the disaster, right? For example, if you know that there's a hurricane coming, you would like to know like where maybe the possible locations of outages in the next few hours, so you can pre-dispatch your repair crews. So that is outage prediction. Yeah, but it is before the disturbance.
Okay, so let's see.
Mhm.
Okay, I think looks like that's all we have questions for. Thank you so much, Dr. Lin. I think we'll conclude the webinar with this, and I appreciate your time this morning with us. And I look forward to a chat with you offline and figure out ways for us to collaborate. Thank you so much.
Yeah, thank you so much again for the invitation. It's really my pleasure to be here. And yeah, if you have any other questions, I mean, for the audience, please feel free to contact me through email, and I will definitely be happy to talk more. Yeah.
Put the slides on YouTube. I made slides, and if you have a copy of the slides, I think it can be shared. We can put it on the YouTube while the recording, when the recording is available. Yeah,
Yeah,
if you
sure.
want. Yeah,
Yeah,
yeah. Okay,
sure.
sounds good.
It should be
Thank
fine.
you.
Yeah. Yeah. Thank you. Have a good one.